My math teacher friends tell me that students always ask them, when am I ever going to use this math that you're teaching me? And that you will be using it in chemistry in high school and also in physics in high school. Actually, engineers use math extensively because, and specifically algebra, allows us to create and use math models to predict what will happen. And this is a much more cost-effective way than just trial and error. An excellent example of this would be the Mars Curiosity rover that NASA sent to Mars. It took 9 months just to travel to Mars from Earth, and they had no way to remote control it once it arrived at Mars and needed to go through the atmosphere and land. And they had to devise an elaborate landing setup with the proper timing, and they had to make all the predictions based on their understanding of physics and the atmosphere of Mars and such. They used algebra to create equations, which are math models, to predict how the physical forces should affect the landing of the Curiosity rover. And then they used those math models to design programs in computers to govern the triggering of all the different mechanisms required for a safe landing of the Curiosity rover. And thankfully, it worked. Recommend the video, so you should go see it. This is going to sound really silly because we've been dealing with variables, I hope, since you were in 5th or 6th grade, at least 7th grade. Quantities that can vary within an equation. We represent them with letters or sometimes symbols from other languages, Greek and such like that. This allows us to have one simple formula that works for a variety of starting situations. I bring this up, I mentioned variables because, again, math teachers tell me that many students of theirs never encounter equations with multiple variables in them, and we will be using multiple variable equations all year long. So I want you to wrap your mind around that from the beginning. I think you're all familiar with the acronym PEMDAS, which is our method. It helps us remember orders of operation as we solve equations. Well, this is when we're substituting in and solving an equation. We first do operations within parentheses, then we take care of the exponents, then we do multiplication or division, and then finally addition or subtraction. However, many times in our physics or chemistry class, we're going to be rearranging a formula to solve for a variable that's buried somewhere in the equation. We need to rearrange to isolate that variable. And so the rules of math require us to use that PEMDAS acronym backwards. We need to do subtraction and addition first, then division and multiplication, and then take care of exponents and then parentheses. So I'm going to lead you through a few examples of these in today's 2 sample questions. Concerning SADMAP and rearranging for isolating variables, there are 2 simple rules that I find myself repeating every year, so I thought I'd give them to you up front. If a term needs to move from one side of an equation to the other side of the equation, we have to perform the inverse operation on it. So if it is added to everything else on one side and we need it to move to the other side, then we need to subtract it from both sides. Or if it's multiplied by everything else on one side, then we need to divide by it on both sides to move it to the other side. And I've kind of gone over the simple rule 2 here in what I just said, which is that if you do one operation on one side of an equation, in order to keep things equal, you have to do the exact same operation on the other side. You cannot do it just in one place and not on the other. And I also have another little acronym for you. So we've done PEMDAS, SADMAP, which is PEMDAS backwards, and now I'm giving you this kind of hokey GFORSS, which leads to a misunderstanding of G's and forces, by the way, but we'll straighten that out later. This is an approach to solving word problems. In physics and chemistry, the math that we do in these courses is really to solve problems that are given to us in word form, which is the way life is. You have to often figure out what you're dealing with and create your own equations and so forth, or substitute into known equations and rearrange and so forth in order to solve. Well, I'm giving you an order of attack for how to solve these problems. The first thing is to write down what you know from the problem, what it tells you and what it implies. That's what I call the givens. Then you need to find a formula that has variables for all those givens that you've been given in the problem or that were implied in the problem, and your formula needs to contain only one missing variable, the variable that you desire to solve for. So all the givens that you know of plus the variable you're trying to find, those are the variables that must be found within the formula you use. Often we need to rearrange a formula in order to isolate the variable we're solving for. And then finally, after we've done that with symbols, we substitute in with the numbers for the variables. We plug in the unknowns. That's what we call substitution. And finally, we can solve using PEMDAS at the end. So rearranging, we use SADMAP. Solving, we use PEMDAS. Okay, here's an example. It says determine the vertical displacement, which means just how far up or down a rock goes if it is launched straight up into the air at 6.5 meters per second and if it lands 4.58 seconds later. Well, what are the givens? We were given its launch speed, its initial velocity, which is 6.57 meters per second. That was written in the question. We're told how much time elapsed, how it landed 4.58 seconds after it was launched. And what's implied in this problem is that gravity is what's bringing the rock down. So gravity's acceleration is a constant. It's negative 9.81 meters per second squared. And what are we asked to find? We're asked to find the vertical displacement. So displacement is what we're looking for. We've got four variables here: initial velocity, elapsed time, acceleration, displacement. We need a formula that works for that. By the way, just going to have a little marker up here showing us that we have completed the givens part of our GFORSS procedure. Okay, here's a formula that has all four of those variables: initial velocity, acceleration, displacement, and time. And it's not a pretty way to have time in there. It's raise the first power here and raise the second power there, but at least it only has those four variables we're looking for. So we found the formula. All right, onward. We need to rearrange that formula. Well, we don't need to rearrange that formula because this time the formula was kindly already arranged to isolate the variable we're trying to solve for, which is displacement. So no rearrangement needed. Next, we need to substitute in our known values. We know what the initial velocity is, and it is 6.57 meters per second. We know what the time is, and it's in here twice, so I'll put it here. It was 4.58 seconds, and also here 4.58 seconds. The acceleration that we already know is acceleration due to gravity, which is negative 9.81 meters per second squared. And so now we've done all our substitutions, and we're ready to go on and solve. And solving means we have to follow PEMDAS, right? So according to PEMDAS, we take care of parentheses first. Well, we don't really have any parentheses to worry about so far. So we do have to worry about exponents, though. We have to worry about this 4.58 squared. So there's our exponent business. We're going to have to multiply everything in this term and in this term, and that gets our multiplication done. There's no division to do, and we're going to add these terms. So there's our addition, and there's no subtraction to do. So we're done. We have solved. So we have solved, and I'm throwing meters on here to show you units because units are going to be very important, but that's another topic, so I'm not going to spend time discussing it right now. But we are finished solving there. We found the vertical displacement was negative 72.9 meters. In other words, that rock that was thrown straight upwards fell from where it was launched. It fell 72.9 meters downward, which is, it's like someone standing on a small cliff. It fell down around 3/4 of a football field's distance downward.